I'm excited. I'm going to introduce very, very briefly, as I tend to do in these, Jobst and Barry. Jobst, I hope this is a correct introduction, that you're the founder and managing director at Cognitech, which is a company that's building AI-based language technology. And you're an MD PhD, so you have an extra degree from all of us here from the University of Göttingen. So with no further ado, please take it away as you like.
I need to adjust a little bit. So this is a quite dense slide, but I will explain step by step. So Barry mentioned that we are talking about complex systems, and we need to understand what is a complex system. Physics became so successful because physicists, starting with Newton and Leibniz, modeled simple systems. And simple systems are systems that are shown on the left-hand side. They have certain properties that allow us to model them mathematically with a high level of exactness and even predict their behavior exactly. And complex systems, they have different properties. And I want to contrast now these two types of systems. So as you can see here, the first property of a classical Newtonian system is that there's a small set of element types. So for example, the solar system has the sun and the planets, and also some satellites of the planets as element types. It has a uniform and isotropic interaction of those elements. So for example, the gravitation, which is the sole force that determines the solar system in terms of how the planets move and how they relate to each other, is the same everywhere, and it is actually moving. Its pattern is isotropic, so it is expanding in all directions in the same manner. So around the sun, no matter where you are, if you are at the same distance, you always have the same amount of gravitation. If you go away, the gravitation gets less, but depending on your radius, how far you are away from the sun, its level is the same everywhere. That's isotropy. Also in the solar system, there's no force overlay. So that means that there's only one force that determines the way the system works, that's gravitation. The phase space is deterministic and ergodic. And can you see the small inset here that shows ergodicity? Is this visible, this small picture?
Yeah.
Good. So you can see that an ergodic system, the elements of the system will over time distribute themselves with equal probability within the available space. So for example, the Earth has a certain orbit around the sun, and its probability of being somewhere in this orbit in a certain amount of time is the same for all the parts of the orbit, if you normalize it at least. And this ergodicity, so there is no, so the Earth doesn't stay longer in one part of its orbit than in any other, and it covers all the parts of the orbit. In a non-ergodic system, the particles or the elements of the system, they don't behave like this. So they may, for example, never be situated in some part of the systems while they may find themselves in other parts. So that means if you pick an example, a sample from such a system. So picking a sample from our solar system would mean to analyze a photograph of how the planets are situated to each other and to the sun at a certain time point. If you have a glass of water, picking a sample means picking up a bit of liquid from the glass. But if you do this in an ergodic system, you can draw adequate samples from the system. But if you do this in a non-ergodic system, you may draw samples which are never adequate, or it's even worse, you can't draw an adequate sample from a non-ergodic system because you don't know which part of the space the particles will cover. Deterministic, that means that all the elements of the phase space obey to deterministic laws. The system is non-driven, which means that there is no flow of energy through the system. So I will explain a little bit better what that means when I explain complex systems, but in the solar system, with regard to it as a gravitational system, there is no drivenness, so no energy flows through the system. There's just gravitation, but there's no, so the heat that comes from the sun plays no role for the way the planets interact with each other or with the sun in terms of gravitation. The system has, classic Newtonian system has no evolutionary properties. So yes, there may, at some point, there may be a new satellite included into the solar system, but these events are very rarely, and especially it would be if the new satellite would come into the solar system. For example, an asteroid would get caught by the gravitational field of a planet and become a satellite of that planet. It would still not create a new type of element, but still it would be of the same type, just an object obeying the laws of gravitation. And such a system, that's very important, has fixed boundary conditions. So for example, if I take the solar system, which is 3.6 parsec away from Alpha Centauri, which is the next solar system, and I could move it a half a parsec towards Alpha Centauri, it would change nothing of the properties of the planets or of the sun, how they relate to each other. So I can abstract away the boundaries of the system without any loss of information about the system. So it has, the system is in a way context free. Of course, if I would move the sun very close to Alpha Centauri, there might be a supernova occurring, but that's a different thing. But basically the system is context independent. Now, if I look at a complex system, such a system depends on multiple arbitrary element types. And oh, by the way, I forgot when I was introduced, I'm also a mathematician. So there are some mathematical aspects to this which I may also explain a little later. And what I'm trying to say here is that the complex system depends on multiple arbitrary element types. So for example, in the human brain, there are billions of elements and many, many element types. There are different interaction types between elements. So that's not only one, but many interactions. And those interactions, they overlay so that several forces act at the same time and possibly interact and overlay. And it's very hard to model this force overlay. And so that's also the case in the human brain, for example, or even in a single cell, in a single cell from an organism, from a mammal, for example. Or actually even in bacterium, many forces overlay. The phase space is non-ergodic. So I cannot state that I can draw adequate samples, for example, from the inside of a mammalian cell randomly. So it's an ordered energy creating structure that is non-ergodic. So it is this case that is shown here schematically on the right-hand side. The driver, these systems, the complex systems, are driven. So that means that that energy is flowing through these systems. Either the energy comes from the outside. That's, for example, the weather system. The weather system is a driven system that is driven by the energy of the sun. And there's a constant flow of energy through this system, which makes it driven. Therefore, it has no inner equilibrium state. It's always changing. It cannot converge to anything. And that's an inanimate nature example, but in animate nature, so in animals and organisms, other organisms like plants or bacteria, fungi, they are able to actually create the energy that drives them. So they are self-driven. Such organisms have also evolutionary properties, so they can all the time add new elements, new element types, new interaction types. A good example for a new element type is a cancer growing in a human being. And they have non-fixable boundary conditions, so they're context dependent. You cannot take a complex system out of its context and imagine that it will still function in the same way that it functions in its natural context, which is, for example, a big problem with animal behavioral biology, because if you take if you make experiments on bees and you want to measure them, probably you have to harness the bee. But if you do this, you take it out of its context, and then you will not measure what the behavior that it would show if it would be unharnessed. Here are some examples of complex systems and whether they have the properties that are listed here. The solar system is not a complex system. It has none of the 7 properties. Steam engine has one property, it's driven. And that's interesting because it's a technically made a machine, and it is driven because if it's supposed to work, it needs to consume energy, and then it has drivenness because energy is flowing through it and making some of its proper behavior unpredictable. For example, I cannot tell which part of water in the steam engine is going to be transformed into steam and will evaporate next, and so on. So in this boiling steam engine, I cannot predict exactly what happens at the molecular level to the water molecules. But other properties I can predict, for example, the proportionality between the amount of energy and the velocity, or the energy, the labor the steam engine can perform. All living organisms are complex systems. And you see here that a virus is not a living organism. It doesn't have the property number 5, which is the ability, which is the energy flow. So it's not driven. And a prion has even less. A prion is, you may remember, it's an infectious protein causing neurodegenerative diseases such as Creutzfeldt-Jakob disease. And you see that a prion lacks several properties of complex systems. It just has the force overlay property and the phase space, non-ergodic phase space, and the non-fixable boundary condition, so context dependence, but it lacks the other properties. So these are these are the difference between simple and complex system. And now we look at what that means for machine learning and artificial intelligence. So on the left-hand side, and that's important because now we're going to talk about intelligence definitions from the artificial intelligence community, and we need to understand the background. What is the problem with their models? So basically, machine learning algorithms cannot model complex systems. And the reason is, first of all, there are many reasons which have been known for a long time why there are problems with machine learning algorithms. So one is that they optimize problem-specific loss functions, and therefore they are not general, but they're just problem-focused. The loss functions are designed by engineers. They are narrowly dependent on the selected training samples and its specific annotation. So I'm assuming that everybody knows what a machine learning model is. If that's not the case, you should interrupt me here. Okay, so if there's nobody interrupting, I could just continue. So they narrowly depend on the selected training samples. They fail if the annotation for identical input is heterogeneous. So if I have the same input, but different outputs, then they will not train properly because it will, mathematically speaking, it's distorting the hyperplane that I'm trying to fit into the hyperspace. They fail on sparsely populated sample spaces. So, and the problem is that most sample spaces are sparse. So if you imagine a dense sample space with 100 samples, which is not much, but let's say we would be in Buffalo University and pick 100 students to measure the body height difference between male and female students. 100 would not be really enough as a sample, but still it would give an indication, a good indication that there is a systematic difference in this property. And that if we say that that's a dense sample space in one dimension, we're just measuring one variable, which is body height, then what is the same density? To achieve the same density with 10 dimensions, we need 10 to the power of 20 samples. That's due to the curse of dimensionality. And that means that most sample spaces in high dimensions are very sparsely populated. And so 10 to the 20 is 100 trillion. So that's really a lot. It's a one with 20 zeros. And so because of this, most sample spaces that we use are very sparsely populated. But the problem is that machine learning algorithms are very poor to work on sparsely populated sample space, because they need for the estimation of the hyperplane, you actually need dense areas of the sample space. Otherwise, the estimate is very, very crude. And that's a very strong contrast to humans. So humans can work very well with sparsely populated sample spaces. They can even, that's actually part of the intelligence, is the ability to adapt to a new situation, which is a non-populated sample space, so to speak. It's like a sample that has never been seen before. And machines are very bad at this in machine learning. So the fifth point is they cannot be guaranteed to move to corrected outcome once an error has been noted. So if you kind of spike your data with corrected outcomes, they may not learn this corrected outcome, because this outcome may be happening in a part of the sample space where learning is impossible anyhow. For example, because it's at the border of the ball of data. And so if it's the border problem is another problem, which I will not go into now, but topologically speaking, most data points in high dimensional spaces are at the border where there are less neighbors in order that are used to estimate hyperplanes in such spaces. They cannot perceive their own failure. They cannot model far-reaching relationships because they usually are modeled on proximity. And there's actually no real way, mathematically speaking, to achieve a modeling of far-reaching relationships, because they are always about distance in spaces. And if the distance gets too high, there are not enough samples available to model this. They cannot model semantics of the mental type. So that's Vergegenständlichung. That means that when you abstract from something on your lying on your table, bananas and apples and peas, and you say these are fruit, or these are apples, different apple types, then they cannot do this, which is why they fail at image and language interpretation, and they don't have sufficient exactness in prediction for critical settings. All of this has been noted many times, and for example by Gary Marcus. But then there are more problems that haven't been modeled, that haven't been noticed before, and I think that's something new about our book. That also complex systems have properties that cannot be modeled with machine learning. So the problem is that ML models require ergodicity. And that's because if you have a non-ergodic system like the one we saw here, you cannot draw a sample that's adequate for training. So because you cannot get a representative distribution of your samples. And so therefore, when you draw from them, you always have a skewed drawing of the sample. That's like only picking, if you want to do the measurement of height differences, only picking people from the basketball team. If you only pick people from the basketball team, then you will have a skewed sample because they are taller than anyone else. And so that's the problem. So complex systems create non-ergodic distributions of data. And so there is no multivariate distribution to draw an adequate sample from. The samples are always outdated. So you are training your machine with a skewed snap when you sample from complex system, and the sample space is always sparse. So that's really tough to imagine or tough to accept, but that's the case because the system is changing so dynamically and it's so non-ergodic that it's impossible to draw an adequate sample. But if you can't draw an adequate sample, you can't train, of course, because training relies on sampling adequacy. Also, you cannot model evolutionary properties. You cannot model non-continuous functions and operators because in a machine learning setting, you need to make a calculated derivative of the operator function, and that needs to be continuous. You cannot, otherwise you can't compute it. You cannot model non-isotropic forces because isotropy is required for all mathematical models of nature. You cannot model, there is no way to model non-isotropy. You cannot model element-specific interaction types because you need basic interaction types that are universally valid. You can't model, it's very hard to model force overlay. You cannot model drivenness, and you cannot model contextuality because machine learning models are context-free. They are always context-free. For them, the only context they know is the sample. But the problem is not only so if you look at the first point that you need ergodicity, that's already bad because you can't get an adequate multivariate distribution. But what's even worse, even if you could, you can't abstract from the context, but you need to abstract from the context in any Turing machine. So Turing machines are always context free because they are just machines standing somewhere in which a computation goes on, but they can of course not take context into account. So points number 8 and number 1 are the toughest points, but the rest is as tough as the others. So that's really hard. And so this, you have to bear this in mind, these essential limitations of modeling complex systems now when we move on. So are there any questions up? I don't know whether in this type of seminar there are questions allowed in between, but if you want to ask questions about these modeling issues before we move to the intelligence problem, then would be a good moment. Okay. Then let's move on. So, but you can still hear me, can you?
Yep.
Yeah, we can still hear you.
Okay, so we have here the standard definition of artificial general intelligence. So we see that this here is from Legg and Hutter. It's a Shane Legg just became head of AI at Google, and Hutter is also very well-known AI computer scientists. Both are actually not mathematicians. We will see in a minute why, how you can see this. Here's the definition of utility of an agent. So the agent is indexed by the letter pi and the environment in which it's operating by mu. So this means that the utility modeled here is specific to one agent in a given environment. And you see that it's actually a sum over rewards that are given at each step. So the I equals 1 to infinity iterates over the steps the agent takes. And this is the utility of the steps it may take. Of course, it's not supposed to work forever. This is just an asymptotic definition. So it receives a reward at every step. This is actually a model from behaviorism. So I think it was Hull who proposed that behavior can be explained by a declining need, and that at each step of your behavior, the need declines. And so if you, for example, if you are very thirsty and start to drink a glass of water, with every swallow of water you make, you decline your thirst. You lower your thirst, and so every time you swallow some water, you get a reward for declining the need. So that's kind of that's where this definition historically comes from, and so it's a reward given for every step of every activity. By the way, even in its provenance, the model was problematic, but we'll get back to this later. And so now there are some problems with the definition. So, basically, just one question: how long do we want to have for discussion? When should I finish? In 15 minutes, or in 20 minutes, or in half an hour?
So I think Barry had said that you were going to talk for around 45.
Good. So I finish in 15 minutes. Very good. So I make this one rather short. So here you see that the definition is, first of all, mathematically faulty because it defines an expectation. It uses an expectation operator. But if you look at a classical expectation operator, it's defined as the sum over the product of the reward times the probability. And so, of course, they want to apply the probability here as well, but it should be applied not to the sum, but actually to the sum of the rewards multiplied by probability. So this is redundant. Yeah, it's like you cannot apply an expectation operator which already contains a sum to a sum. It makes no sense. And I'm very astonished that they didn't notice this. Yeah, but they didn't think it through. It's kind of sad because they print this equation everywhere. It's just mathematically faulty because the operator, it's just grammatically wrong to apply this operator to such a sum. But anyhow, if we ignore this problem of the definition, So the real definition should be they should get rid of the operator and just put py behind the ry. Then the definition would be correct. And this probability is of course smaller than 1, so that you obtain that you can obtain an overall smaller than 1 sum as they require here. So anyhow, if we ignore this problem, and I think as a mathematician, I kind of suffer under such bad usage of operators, and therefore I realized it. And anyhow, so in simplified terms, if we ignore this mathematical problem of the definition, it says that an agent pi reacting to an environment mu obtains a finite reward, which corresponds to the, and the finiteness is defined here that smaller equal to 1, which corresponds to the expectation of reward it receives over all steps it undertakes. And so, of course, reward here has no meaning for the machine. It's a mathematical concept to express an optimization problem. It's very related to the loss function that you know from machine learning. So it's just another way of formulating a loss function in a positive way. So loss function kind of calculates how much is the difference between the real outcome and the predicted outcome of the algorithm, whereas this is kind of a gain function. It tries to optimize, whereas the loss function wants to minimize, wants to find a minimum. This function is supposed to find a maximum, but it's the same. Mathematically, it's quite close to each other. So it's just a way to express an optimization problem in the language of classical behaviorism. So if we now look at, so this is one agent in one environment, but what's the intelligence? The intelligence is this. It's the intelligence of agent pi is the sum of the utility that the agent achieves over many environments. And U is actually the set of environment descriptions that the algorithm can process. So if that's, for example, a chess playing machine, then these would be all the positions on the chessboard. And then the utility, the intelligence would be the ability to achieve maximum utility given different positions on the chessboard. But if it's a universal agent, it would be anything the universal agent can deal with. And so for Robocop, that would be many more situations than just situations on the chessboard. And so here you see this variable again, this utility again, and now there is a Kolmogorov complexity function multiplied with it, which just penalizes the utility term by the complexity of the environment description. So mu is not really the environment, but it's the way the environment is expressed as a binary, as a Boolean vector, as a binary vector. And if this binary vector is very long, the agent gets penalized and gets less utility. And that's because, of course, it's not only that there should be, so if you could make an infinitely long description to yield a higher utility, that should be forbidden. So this is to ensure that the agent also has efficacy in obtaining the utility. So it cannot compute it could compute forever to get here, as you see, to get the utility, but that's penalized to avoid this. There's this penalization factor. So that's basically a very classical computer science definition of utility. It just shouldn't be confounded with intelligence. So to say this is intelligent is nonsensical, as we will see in a minute. But it's chosen to yield the most efficient possible algorithm, that's for sure. So it's kind of computationally correct to use this Kolmogorov complexity function term. The problem with the definition is that it is actually defining the intelligence of an amoeba. So the verbal definition they give is intelligence measures an agent's ability to achieve goals in a wide range of environments. So this definition just captures one part of intelligence. So for example, Scheler, who gave a very good definition of primal intelligence, which is basically the intelligence animals have, is that they should adapt to new environments. It lacks three further constitutive properties of such a definition, which is the suddenness of the adaptation, the untrainedness of the adaptation, and the novelty of the situation. And so the definition is somehow too narrow because animals can do more than achieve goals. Yeah, they can actually react to completely new situations suddenly without having ever been trained to such situations. So dogs can do this, for example, or birds can do it. And but then it's also too broad because it allows C. elegans, a worm that has just 1 millimeter of length and 1,000 cells and only 300 neurons, would then be intelligent because it lives in, it can forage and reproduce in many complex environments such as fruits, vegetables, mushrooms, compost, soil, and so on. It can also even crawl into slugs and use them as migration vectors. So it's really, so it would then already be intelligent. Even an amoeba, which is a single-celled eukaryote, here is a picture of Chaos caroliniensis, one of the first amoebas that were described in the early, I think, 1910s. It's a picture from 1910, I think, and it shows the way it moves here and changes its shape. So it's also intelligent according to this definition. Well, I wouldn't say an amoeba is intelligent, but according to this definition, it is. Now, the next problem is perception. So they use mu as a measure of the complexity of environments. And that presupposes that environments can be represented by using a binary vector. But in artificial environments like a chessboard, a binary representation may be adequate, but in natural environments, the signals that get observed, like here this tiger observing prey, these signals emanate from complex systems and they require interactive interpretation and reassessment. So the tiger adjusts all the time to the moving targets of his prey. He reacts to them. He actively moves and does active perception. For him to speak in the terms of ecological psychology, Gibson, this is actually an affordance. So the situation presents him with an affordance, which is conveyed by information that he's actively perceiving, and this observation needs to be adapted. The interpretation of the information depends on implicit mental material like experience of the animal. So young tiger who's learning to chase, to hunt, will process this information differently than the adult tiger. So the tiger acts all the time. It's not a static activity. It's a dynamic process. It's explorative and it provides us with affordances. And just a side remark. So one affordance. So for example, somebody may see a teacup as a means to drink a liquid, but you can also see it as an affordance to throw the cup at someone, depending on the situation you're in. And so this is completely ignored by the artificial intelligence definition of perception. It also depends on more than just sensory input. It requires the observer's purposeful activity. And the definition they use doesn't capture any of this. Here's a more difficult example of observation or perception, which I'm not going to discuss now because I need to stop in 6 or 7 minutes. The other problem is that activity is also much more complicated, and activity patterns are not captured adequately either by the definition, because the reward that is modeled is actually inadequately shown. And I want to talk a little bit about reward. So the core problem is that there must be a reward at every step in this definition. But if you look at a rat trying to run out of a maze to obtain food at the exit of the maze, it will actually not at every turn it makes receive a reward. It will receive the reward only when it exits the maze. So you cannot. How can you assign rewards to steps? It theoretically sounds good, but in practice there are many situations where animals don't get a reward over a long time or even get a negative stimulus to obtain at the end the reward. What's even worse is that rewards, intelligent systems are complex systems and their environments, so the reward chain that you would need would itself have to be complex. But we have no way of creating chains of complex signals. So if we have an emanation of complex signals from a complex source, we don't know how to model this. So we can't create a pattern of such a reward chain. So to deal with a complex situation created by complex systems, we need a complex reward pattern, but we don't know how to model a complex reward pattern. And surely it's not just the sum of weighted rewards. It's something much more difficult, and there's no way to model this. I think that's completely overlooked by this community. It works in chess and in the game of Go, and even in some versions of poker when you take the human factor out, but it doesn't work in real life. So to finish, I want to not to sound too pessimistic about AI, that you can achieve a lot with AI if you get it right. And getting it right means that you actually are aware that machines can only do that what they are told. But you can describe what they are told in such a complicated way that you can get at the end a very, very sophisticated behavior. And you can do this through engineering by composition, because here you see a chain of functions and operators that together achieve a very attractive outcome. And they can do this because you take a series of operators and functionals that you chain together, and this operator takes an input, creates an output, gives it to this functional, and so on until you get the final result. And such a chain, you can also give those functions operators prior knowledge. You see here, these Greek letters symbolize prior knowledge that has been given to the functions and operators so that they can achieve some level of contextuality. So you can simulate contextuality by giving them prior knowledge. And this can work for differential diagnosis applications in medicine, but it can also work for, let's say, robotic assembly. So there are many, many examples where this works very well, but it's a conscious effort by the humans to actually get this into machines, and they will not create such chains of compositions by themselves. Or if they do it by themselves, they will not be able to manifest any intelligence in the way that we understand intelligence of a bird, a dog, or a cat, let alone the intelligence of a human being. And so to sum up, the key problem is that this definition of intelligence neglects all the aspects that make intelligence what it is: perception, activity, intention, and the true nature of reward. Nothing of this is modeled here. And it's just actually another way of formulating a loss function. And it's kind of pathetic that a scientific community can take a reformulation of a loss function, famous people like Schmidhuber, who also supports this definition, and then say this is our way to define intelligence, because it's mathematically very thin. And for sure, it has nothing to do at all with human or animal intelligence. Thank you for your attention.